Dear students, today we are going to discuss control charts for attributes. Already we have completed the discussion on control charts for variable data. You can ask me, what is the need for control charts for attributes? Though variable control charts, that means X bar and R charts, are powerful tools for the diagnosis of quality problems, they do have a certain limitations. X bar and R charts cannot be used for quality characteristics that are attributes. That means the data obtained by counting, you cannot apply control charts for variable data. For example, the characteristics such as incorrect color, number of cracks are not measurable, and variable control charts is not applicable. And X bar and R charts can be used only for one measurable characteristics at a time. For example, if a machine has 50 dimensions, therefore you should construct 50 X bar and 50 R charts. So this method would be too expensive and time consuming. In order to avoid the above limitations, the control charts for attributes are used. Control charts for attributes monitor the number of defects or fraction defects rate present in the table. So before we start discuss about the type of control charts for attribute data, first let us understand two important concepts: defectives and defects. I'll explain you with an example. Take a product, say a table. A table has several dimensions. Consider only 4 dimensions for this example. One is height of the table, weight of the table, width of the table. Okay, so for producing or manufacturing the particular table, first you should set specifications or the standards. Then only you can produce the product according to the standard set. Say the length of the table is 1 meter, height of the table is 500 centimeter, that means half meter. Okay, and weight of the table is 5 kilograms. Okay, width of the table is say 20 centimeter. So those are some of the specifications you set for producing a table. After the manufacturing of table, the product dimensions are measured whether they fulfill the specifications or standards set for the product. After the product is being manufactured, you measure the length of the table. If it is exactly 1 meter, it is okay. If it is more than or less than 1 meter, then the length is one defect. Similarly, you measure the weight. If it is more than 5 kg or less than 5 kg, it is another defect. Okay, measure the height of the table. If it is more than 500 centimeter or less than 500 centimeter, then it is another defect. Okay, if a particular quality characteristic does not meet the specification or standards set for the manufacturing process, then that particular characteristic is called as a defect. Okay, defective means if any product, the entire product has one or more defects, then the whole product is said to be a defective product. For example, the table may have length as a defect, weight as a defect, height as a defect, or width as a defect. Okay, it may have one or more defects. But even if it has one defect, the entire table is said to be a defective table. So this is the difference between these two concepts. Because the types of control charts for attributes are 4: P chart, NP chart, C chart, and U chart. The P chart and NP charts are constructed or used for the data about defectives. Another name is non-conforming items. Both are same name. Whether you say defectives or non-conforming items, they are same. And if you select a number of samples for measurement, if the sample sizes are variable, then you can apply P chart. If the sample size is constant, then you can apply NP chart. But if you have a data about number of defectives, you can apply either P chart or NP chart. P chart is when sample size is variable, NP chart is when sample size is constant. That means equal sample size for all the samples. If you have a number of defects data, you can apply either C chart or U chart. If the sample size is constant, apply C chart. If the sample size is vary, then you can apply U chart. First, let us discuss about P chart. P chart is number of defectives data when the sample size is variable. So here you are going to construct the P chart for fraction defective. That is the ratio of the number of defective articles found in any inspection to the number of articles actually inspected. That means P means fraction defective, that is equal to NP divided by N. Here NP is the one symbol, it is not N multiplied by P. NP is the one symbol. NP means number of defectives in a sample divided by N is that particular sample size. Okay. Where average fraction defective is P bar. Okay, that is calculated summation of NP divided by summation of N. So if you have calculated P bar value, then central limit for P chart is P bar. UCL for P chart is P bar plus 3 into P bar into 1 minus square root of P bar into 1 minus P bar divided by N. Here the N is average sample size. It is not one particular sample size, it's an average sample size. I told you samples have a different sample sizes. Okay, so you have to take average of the given samples. That average sample size is N. Here LCL is P bar minus 3 into the square root of P bar into 1 minus P bar divided by N. Here also N is the average sample size. Okay, let us solve one problem. Problem given here is following is the record of the defectives observed during the inspection process of an automatic machine producing small capacitors of standard size. Find the 99.7% control limits for the process. That means control limits for the process you have to calculate. Draw the control chart and comment on the state of control in the process. Here they have not mentioned construct P chart, NP chart, C chart, they have not mentioned anything. So if in case if the problem they don't mention any particular control chart, you have to apply the simple rule as I told you, whether the defectives data or defect data given. Here in the problem it is the number of defective capacitors. So defectives data is given. Look at this sample sizes vary. So it changes 25, 50, 45, 55. There is a sample size vary from one sample to another sample. In that case you can apply P chart. Okay, P chart is number of defectives data with variable sample size. So P chart is the appropriate chart. If the problem, if they give specifically about P chart, NP chart, C chart, U chart, you go for the particular chart irrespective of the data given. If they don't mention particular chart, then you have to use this simple rule to identify the appropriate control chart. First you have to calculate the average sample size N. Average sample size is add all the sample sizes of all the samples divided by total number of samples. So for 15 samples the sample sizes are added here divided by total number of samples is 15. So 630 divided by 15 you get 42. Next you have to calculate P bar value, that means average fraction defective. Here summation of NP divided by summation of N. Summation of NP means total number of defectives in all the samples divided by total number of items inspected in all the samples. So number of defectives for each sample is given in the table. You have to add all those values divided by total number of samples items inspected in all the samples. How many samples? 15 samples. In each sample an average they have 42. So 15 into 42. Well, 630 total items in 15 samples divided by total number of defectives 44. So P bar is 0.070. So you have calculated P bar value, you have calculated average sample size. Now you can calculate the control limits. Central limit is p bar, that is 0.07. UCL is p bar plus 3 square root of p bar into 1 minus p bar divided by n. N is average sample size. P bar is, average sample size 42. So UCL is 0.188. Similarly, calculate the LCL value. You get minus 0.048. If you get a negative value, you have to take it as a 0. You have to assume that as a 0, because attribute data is data obtained by counting. When you count the data, you won't get negative value. Minimum you will get 0. If nothing is there, you will get 0. You won't get negative value. So you have to assume that as a 0. Next, to draw the control chart, as I told you, whatever the chart you construct, in the y-axis you have to take that particular value. P chart means in y-axis you have to take p value. In x-axis you have to take sample numbers. Here p means fraction defective. Okay, fraction defective p is np divided by n. Np is number of defectives in that particular sample divided by that sample size, the particular sample. So this is the p value that is not directly given in the problem. So you have to calculate the p value for 15 samples, fraction defectives. So for example, sample number 1, number of defectives 3, sample size is 25. So you will get 0.12. Similarly, you have to calculate for the 15 samples fraction defectives. So in the chart, fraction defective is taken in the y-axis, 0.01, 0.02. Here 1 centimeter equal to 0.01. That is the scale taken. Say they started from 0, 0.01, 02, 03, 04 up to 0.20. In the x-axis they have taken sample number. Okay, whatever the chart you construct, you have to take that value. P chart means p value, NP chart means NP value, C chart means C value, U chart means U value. You have to take it in the y-axis. In the x-axis it's always same, sample number. Okay, so next you have to construct the draw the 3 lines. LCL is 0, so x-axis is the LCL. Then CL is 0.07. 0.07, you draw the straight line parallel to the x-axis. So CL is 0.07 and UCL is 0.188. It is almost close to 0.19. 188 means close to 0.19. So draw a horizontal line parallel to the x-axis. UCL is 0.188. Now you have to plot all these p values you have calculated for 15 samples. Sample number 1, p value is 0.12. So sample number 1, p value is 0.12. For sample number 2, p value is 0.1. Sample number 2, p value is 0.1. So those 2 points are connected with a straight line. So next, third sample 0.02. 0.022 is slightly above than 0.02. So here, so join second and third point. Similarly, third and fourth point. Similarly, you have to plot all these values. So you have plotted all the 15 points on the table. Connect the subsequent points with a straight line. So you will get the control chart like this. So now you have to check whether the process is under control or not. Check whether all the points are within the UCL and LCL. UCL is here, LCL is 0. So all the points are within the control limits. Okay, no point is outside the limit, that is above UCL or below LCL. It can be on the line. Okay, it is 0, it is on the line, it's not below LCL. So in the case, all processes said to be under control. All the p values are within the UCL and LCL. The process is under control. So you have to comment the process. It can be seen from the chart that all the points lie out inside the control limits. Hence it can be said that the process is in control. Okay, I hope you understood.